This is Lab Report 5, Motion of a Falling Slinky. The main goal of this lab is to evaluate the forces involved in the motion of the bottom of a slinky dropped from a certain height. With the analysis, I will be comparing a computational model and an experimental model of the motion. I will be analyzing the drop of a slinky from a Veritasium video. With the evaluation of the forces involved, it is easy to understand the effects the drag force and the force of gravity has on the position of an object. The main principles that will be introduced in this lab include Newton's first law and Newton's second law. As you can see in the video to the left, the top of the slinky is dropped, while the bottom of the slinky initially has no velocity. However, over time, the top of the slinky reaches the bottom slinky, and it begins to move. This portrays Newton's first law as an object that will not change its motion unless acted on by another force, explaining how the bottom of the slinky begins to move. The main forces we will be evaluating in this lab are the drag force and the force of gravity from the beginning motion of the spring. Before analyzing the code, there are a few physics principles to introduce. The forces involved in this lab include the force of gravity, which is known to be the mass of the slinky times the gravitational constant of Earth, and the drag force, which is known to be the proportionality constant times velocity of the object squared. The foundation of these equations, especially the force of gravity, follows Newton's first law of motion, where force is equal to mass times acceleration. Moreover, in order to extract conclusions from this lab, there are a few assumptions that have to be made. Due to the fact that we were not given the mass of the slinky, I searched up the average mass of a slinky and concluded it to be 0.218 kilograms. Because we were also not given the height of the slinky, I used the span of a man's hand and used it for the main basis of measurement. Therefore, with both of these estimates, there may be a few errors in scale, but the general shape should be similar. Another assumption I've made is that there is no spring force involved based on the fact that I'm analyzing the bottom of the slinky and its position as it falls based on drag force and the force of gravity. In my code, I began with initializing the conditions such as the mass of the slinky, which was 0.218 kilograms, the initial position, which was negative 2.22 times 10 to the negative 16th in the x, negative 8.775 times 10 to the negative 3 in the y, and 0 in the z direction, and the initial velocity, which was 0 meters per second. Then I plugged in the gravitational constant as 9.8 meters per second squared, and for the proportionality constant, we were not given enough information, so it was a process of guessing and checking in order to find an appropriate proportionality constant for the magnitude of the drag force. For my first while loop, I included the forces to be equal to each other in this time frame because the net force had to be 0 in order to display the unmoving bottom of the slinky. Moreover, I included the position update formula and the velocity update formula in order to update both values for each time interval. As you can see in my second while loop, I included the force of gravity to be negative as the mass times the gravitational constant times the unit vector for the positive y-axis, and I included the drag force of negative bv squared times the unit vector of the velocity vector. The net force would be the sum of these two forces. Once again, for this time interval, I included the position update formula and the velocity update formula in order to update both values for each time interval. As you can see in this experimental model, the bottom of the slinky stays at its relative original position until it suddenly starts to drop, as it is propelled where the force of gravity and drag force are working in action. In the computational model, the bottom of the slinky also stays at its relative original position until it suddenly starts to drop as well. Although the scaling is off, as I've mentioned before, the assumptions I was required to make may cause a big error in the scaling, as the measurements of distance and mass are off. However, the graphs look fairly similar with a similar relative shape. Thank you for watching this lab report on the motion of a falling slinky.